Hi everyone. Today I'm going to talk about hydrohalogenation. Hydrohalogenation is an addition reaction using a hydrogen halide. So we're talking about things like hydrogen chloride, hydrochloric acid, hydrogen bromide, hydrobromic acid, and hydrogen iodide, hydroiodic acid. Now this is an addition reaction. If I use a small, simple molecule like this, where I've got a double bond, there's nothing else. I react it with hydrobromic acid. I'm going to add the hydrogen to one carbon, the bromine to the other, and one of those two bonds is going to go away. So we get something like this. When you're looking at organic reactions, you want to know how the mechanism works. The mechanism is what bonds are breaking and what bonds are forming in what order to get us from the end from where we started at. And it always helps us understand why things are happening. Because if we know why something's happening, we can predict what's happening. So in this case, I've got a carbon-carbon double bond. And I've got my HBr. The double bond, which is electron rich. Why is it electron rich? Well, if we think about it in the simplest way, there's 4 electrons there instead of a normal 2. That's more than what we'd expect. It's going to attack the thing that is electron poor, the thing that doesn't have as many electrons. Hydrogen only has 1 electron and it's attached to something more electronegative. If it's more electronegative, it's pulling those electrons towards it. So hydrogen didn't have much to begin with, and it's getting pulled towards bromine, which makes this a little bit positive, a little bit poor on electrons. So what happens, the extra electrons are going to attack hydrogen because hydrogen needs more. But since it only maxes out at 2 electrons to come in, these 2 have to leave. Where are they leaving? They're going to go to the bromine because it's more electronegative. That bromine's already pulling on those electrons, so when this breaks, it makes sense that it goes to the atom that wants them more. So that bond breaks, and those 2 electrons go to the bromine. Now, when that happens, these 2 electrons are now making a bond to hydrogen. That's what we see right here. The other carbon, because that double bond was shared between 2 carbons, the other carbon is now missing electrons. It had 8, 2, 4, 6, 8. It now has 6, 2, 4, 6. That means it's a carbocation. It's very positive, it's very reactive. What's this really positive, really reactive carbon going to do? It's going to look for something with lots of electrons. Bromine, if you look at it on the periodic table, it's a big atom, lots of electrons, but even our little Lewis structure here, it's got 2, 4, 6, 8 electrons and a negative charge. So it's got a lot of electrons and it's got a negative charge. That's electron rich. So electron rich, electron poor, negative attacks the positive. So negative attacks the positive. When it does that, it makes another bond. What do we get from this? We get that product we ended up with. Hydrogen bonded to one carbon, bromine added to the other carbon. So that's the simple form of hydrohalogenation. Now the structure I started with was symmetric, means it's the same on both sides. What happens when these things are asymmetric, when one side is different than the other? Well, let's take a look at that. I've got a carbon-carbon double bond. On one side, I've got two hydrogens. On the other side, I've got a hydrogen and a methyl group. So left side is different than the right side. If I react this with one of the other hydrogen halides, like hydrochloric acid, what we saw before, we know one of those bonds is going to go away from the double bond. Double goes to a single. And we add a hydrogen to one side and a chlorine to the other. But the two sides are different now. So there's two different ways this could add. So this could add in one of two ways. The chlorine adds to the end carbon. That's this one right here, the one that had two hydrogens on it. If the chlorine adds to this one, then the hydrogen has to add to this one here, the one that's attached to the other carbon. Or we can flip it. Hydrogen adds to the end carbon, chlorine adds to the middle carbon. Those are the two possibilities. Now what we see, if you run an experiment with this, you'll see one of these is formed a lot larger yield than the other. You see this one here with the chlorine on the carbon that's got more carbons attached to it. We call this the major product. We get a lot of that, but why? Always helps to know why. So how do we find why in organic chemistry? We look at the mechanism and we try to find something different. So I'm going to walk through the first step of the mechanism because I got a double bond, I got HCl, it's going to add a hydrogen regardless. So when I draw my mechanism and I show my arrows, the arrow pushing the movement of electrons for this first step is going to look the same regardless of which one of these I make, but the product that's formed is going to be different. So my double bond attacks the hydrogen because it's a little positive, and these bonding electrons go back to the chlorine because the chlorine is pulling on those electrons harder. This is going to give me one of two intermediates. Either the hydrogen adds here or the hydrogen adds there. So I'm going to draw both of these so we can see what we've got. If the hydrogen adds to the end carbon, we get this intermediate here. If the hydrogen adds to this middle carbon here, I get this intermediate here. They look very similar. They both have a carbon with a positive charge, and that's really the big difference. So we have to ask ourselves, well, why is one of these better than the other? Well, this comes down to what we call carbocation stability. A carbocation is just simply a positively charged carbon. Not all carbocations are created equally. Some are more stable than others. What we see is that the more carbons attached to a carbocation, the more stable it is. If it's got more hydrogens, it's not going to be nearly as stable. For example, if I had a methyl group, a carbon with 3 hydrogens, and that carbon was positive, that wouldn't be very stable at all. But what we see is that as we add more carbons to it, it gets more stable. This carbon is attached to another carbon, it's more stable than this one here. We would call this a primary carbocation, primary like first one, because that carbon's attached to one other. If I had two carbons attached to it, like this, that would be a secondary. Secondary is going to be more stable than primary. If I keep replacing these, I've now got three carbons attached to that carbon. That's a tertiary carbocation. That's even more stable. So the more carbons attached to it, the more stable it is. So if I look at these two, this carbon is primary because it's attached to one other carbon. And I'm going to put a 1 with what looks like a degree sign there. That's a symbol we use a lot of times for primary. That's a primary carbocation. One carbon attached to one. This carbon is secondary. Secondary because that one carbon is attached to two others. One on the right, one on the left. As it's got more carbons attached to it, it's going to be more stable. So if I look at the two possible intermediates forming, I have one that's not very stable, and I have one that's a lot more stable. What you're going to notice in organic chemistry is that stability runs a lot of these reactions. It's going to do things that are more stable. If it's lower energy, it's more likely to happen. So I can make something really high energy that's less stable, or I can make something lower energy that's more stable. It's going to take the easier path. It's going to make the one that's more stable. So if this one is made in preference to this one, then my chlorine, which is electron rich, remember, because it's got lots of electrons, is going to attack that carbon. And we get that product that we call the major product. It's the major product because it's the one that's most likely to be formed. It's most likely to be formed because this hardest step to perform is going to take the easier path, the one that makes the more stable intermediate. So this is why we see what we do. I'm going to finish this with a name. We name these two types of addition products. The product here that was our major product we call a Markovnikov product. A Markovnikov product, there's a lot of ways to describe it. Might be the easiest way to remember it is that if I've got two carbons on my alkene, a Markovnikov product is the one where the hydrogen adds to the carbon that already has more hydrogens. So if I look at this, there's two hydrogens here, there's one hydrogen here. Markovnikov goes ahead and puts another hydrogen where there's lots of hydrogens. He finds his friends, he gives more hydrogens to his friends. The not hydrogen, chlorine, bromine, iodine in this case, other reactions it might be OH, you'll see lots of these. But the other thing is going to add to the carbon with fewer hydrogens. So that's a way to think about or remember Markovnikov. Now we just saw why Markovnikov happened, but if you're just looking at a reaction going, where does this add? That might be a way to do it. So our major product is the Markovnikov. The one that's not Markovnikov, wait for it, we call it anti-Markovnikov. So if it's not Markovnikov, it's anti-Markovnikov. So our hydrogen goes where there's not as many hydrogens. My not hydrogen goes and finds more hydrogens. So Markovnikov versus anti-Markovnikov. Now if you found this whole thing useful and you liked it, please make sure to like and subscribe. Why Chemistry?